Aloha. In this problem, we're shown a drawing similar to this where we have a pipe system going into a brick building. And we're told that we're just given values for information at the start of this system at street level as well as at the top height of the building. So the height of the building is 16 meters. And the gauge pressure, which is the actual pressure minus the pressure of the atmosphere, is 3.8 atmospheres. That's a standard unit in terms of the Earth's atmosphere at sea level. And I'll label this PG for gauge, and this is the in pressure here at the start of the system at street level. And it has a velocity coming into this system at 0.78 meters per second. So it's good to just write all this given information down in terms of variables and systematizing with labels like in and out. Because ultimately we're going to be using Bernoulli's equation, which is like an energy conservation equation for the input and the output of this system here. The diameter, the larger diameter is here at the beginning of this pipe system. That's 5 centimeters. And I just label it a capital D to emphasize that it's the bigger one. But I'm still reading, this is the input side. The output side, the diameter is smaller. This is at the top of the building, 2.8 centimeters. And I think that's all of the given information. And we want to find the output velocity as well as the output gauge pressure. So this is at the top of the building. And we know that we can start by writing Bernoulli's equation. So the input gauge pressure plus rho g y0, which we can take to be 0. We can just define this as y equals 0 here, and this part p y equals h plus 1/2 rho, where rho is the density of water. So rho, what is rho water? This is just a known constant, so you can find this earlier in chapter 10 in the textbook, 1,000 kilograms per meter cubed. Times the input velocity squared. And we have this equals the same quantities on the other side of the pipe system. And we're told that the faucet at the top of the building is also open to the atmosphere. So when we're looking for the gauge pressure, we know that it's exposed to atmosphere. So both sides, they are both experiencing atmospheric pressure here. And this is going to be a useful equation. We have the output pressure and we have the output velocity, but this is one equation, and all the other variables are known, like the input pressure, the density of the water, g is a constant of nature, acceleration due to gravity, input velocity, the height h, but one equation with two unknowns isn't enough to solve for those two unknowns. We need another equation, and we can just think more about this problem, and we know that there's going to be, we can apply the continuity equation for this fluid flow here. So we know that the area times the velocity will be constant. This is like the volumetric flow rate will be a constant. So we know, we could say that A1, which is, or maybe AN, this is the cross-sectional area at the input times the input velocity will be the same as the output area times the output velocity. So basically this pipe is wider, we have a constant input velocity, and that's going to shrink down. So we expect that the output velocity is speeding up as it's, maybe slowing down as it's kind of squeezed into a smaller pipe. So we we'll see it's, well, yeah, I think it should speed up. But we can just calculate this out. We can solve for the output velocity, which is something we want to know. So we can plug this into Bernoulli's equation and then just have one equation with one unknown. You can just solve for that algebraically. So this will give us the output velocity. And we're not told the areas, but we're told the diameters of these pipes. We know that since it's a diameter, it must be circular. And the area is pi r squared, where r is the radius. So that's the diameter over 2 squared. And we see they can cancel out the denominator of 2 squared as well as the pi. Just separating this. And then we can just plug in, because we have the equation that the input diameter over the output diameter squared times the input velocity. So we can just keep these in terms of centimeters because that's units going to cancel out. So our final answer for the output velocity should be about 2.5 meters per second. And the input velocity was about, we were told, was 0.78. So it is speeding up through this smaller pipe. And then we want to look back at Bernoulli's equation and rearrange it. So now we have this as another known quantity that we can plug in. So we wanted to write this as an equation for the gauge pressure at the top of the building, which I labeled out. So on the other side of the equation, we had the pressure at street level. We don't have a potential energy term because we set the height there to be 0. We have half rho V in squared. And then from the other side of the equation, we subtract the output velocity term and rho GH. Just rearranging that a little bit. And now we can just plug in these numbers, all of which are given or we just calculated V out. 3.8 atmospheres, and we can convert from atmospheres using, to write this in newtons per meter squared, which is a Pascal. So you want to add up all these terms in terms of pascals. We can still write the final answer in ATM and just convert back. So this is the velocity squared. You want to use as many digits as you can here. Just keep that in your calculator and then just approximate at the end to get the most accurate approximation here, just in the final answer. So this is the density of water. G is 9.8 meters per second squared. We're told that H is 16 meters. So this will be an answer in terms of newtons per meter squared, because here we have velocity squared. So that's a meter squared over a second squared there. And a kilogram meter per second squared over meter squared, that's a newton meter squared, because a kilogram meter per second squared, that's a newton. It's a unit of acceleration, mass times acceleration. So that's a newton. And you should get about 2.25 times 10 to the 5 newtons per meter squared, which is a Pascal. And we can convert that then to atmospheres if we want. So it's about 2.2 atmospheres at the top of this building. So these were the two answers we were looking for: the output velocity and the output gauge pressure.